Hi. I'm a PhD student in ETH. I'm supervised by Professor Kammer and Professor Fink. Today, I would like to introduce our recent work on learning physics-consistent particle interactions. So in engineering, we study the mechanical properties of different materials and also the dynamic process happening in the real world. And one representative way for this physical system is a particle-based representation. So here, basically, here I want to show two particle-based simulations for these systems. The problem here is that to understand and model these physical systems, we need to know the information about the pairwise interaction between particles. However, this is not possible in many real cases. So the research question here is that how to know the pairwise interactions. And our idea is to use machine learning. The difficulty here is that, as mentioned before, we do not have the ground truth information to guide us to train the machine learning model in the supervised way. What we have here is that we can observe the trajectory of particles at different time steps, which includes position and velocity, and also acceleration of particles. Besides, we have some information about the particle properties. Then at every time step, we can naturally represent the particles as a graph, where the nodes represent the particle and the edges correspond to their interaction between particles. The graph representation enables us to use the graph neural network approach to extract the pairwise interaction from the trajectories. Basically, the method places a neural network for every edge, which outputs a predicted interaction, which basically is the pairwise force between these two particles. And then it uses another neural network on every node. This neural network takes the inputs of all incoming messages and the node property as input and outputs the predicted acceleration for every node. Finally, the model is trained to predict the ground truth acceleration per node. After training, the output of neural network on every edge is believed to be the pairwise force. However, after running the experiments, we found that the inferred pairwise force doesn't match to the ground truth pairwise force. For example, this toy example, the left figure is a 2D spring force. The orientation of vectors should point to the center or away from the center. And the color here indicates the magnitude of the force at different positions. The right figure is a predicted force by the graph neural network. And we can see that the orientation of these vectors, which basically is the force field, doesn't match to the ground truth. And also the color has difference. The problem here is that the output space of the edge neural network has too much freedom. So even the final prediction matches the ground truth acceleration well, the output of edge neural network may not necessarily be the pairwise force. So our idea is that we restrict the output space of the edge neural network. We do this by substituting the neural network on node part by the deterministic physics operator. For example, if we target to learn the pairwise force, then for every node, we sum up all incoming messages and then divide its mass. So if the final output is acceleration, then the messages should correspond to the pairwise force. And otherwise, if we want to learn the pairwise potential energy between any two particles, then we compute the partial derivative of all incoming messages with precision, and finally we divide the mass. Now let's see the results. Okay, remember that this is a previous results, that the pure data-driven graph neural network doesn't match to the ground truth. And our method, the results of our method here, it matches the ground truth well. For example, if we examine the orientation of the vectors and also the colors. Finally, okay, let me make the summary that the method is also applicable to different kinds of interactions other than this 2D spring example. And besides, we test the method that it can be generalized well to larger system, while the model is trained on a smaller system. And finally, the model is robust to noise input, like the noise precision. This is important because in the reality, the measurements will always have the noise. And the details can be found in our paper. And thank you.